Let's bring together the two ideas that we've been looking at in the previous couple of sections. So a set of vectors S is a basis for a vector space V if and only if it is both a spanning set for V and a linearly independent set. So let's think about what these two concepts mean both in the context of a particular set of vectors and this defining equation. So given a vector B, can we solve this equation right here? Well, so the property of being spanning says that, so if S is a spanning set, that means that a solution to this equation below exists. Okay, there's enough things in S, or enough of the right type of things in S, that we can solve that equation. So that equation can always be solved. As opposed to linear independent, which means that at most one solution can exist for that equation, right? So if you remember, S is about how there is no redundant information. So there's no redundant information in S. It's somehow minimal. And at the same time, spanning set, this means that there's a sufficient amount of information in the set S that we're able to represent anything in terms of it. So what we really have here is that the first criterion, that S be a spanning set, this is an existence criterion. There always exists a solution. And the second one, for linear independence, this is a uniqueness criterion. So taken together, so if S is a basis, actually let's change this to an if and only if type statement, because it is. S is a basis if and only if there is a, or maybe let's say, just to harp on the point, there exists a unique solution regardless of what vector B we have chosen. Okay, so that is the notion of basis. Okay, so now let's talk about why a basis is a great thing to have. And this is basically why we do linear algebra. The fundamental idea is that we can do everything in terms of the basis, and that greatly simplifies everything. We can express solutions in terms of a basis, we can describe transformations in terms of a basis, and so forth. So let's go with transformations for now. So suppose we have a linear operator. Okay, so this is a function that takes vectors in V to other vectors in V. Okay, so precisely it means that if we apply T to a linear combination, it's the same thing as applying T to the individual components first, taking the scalar multiples and then adding them up. So taking the linear combination after applying the transformation. Okay, so and the fundamental examples that we're working with, we have the linear algebra example, multiplication by a matrix, and we have the differential equations example, which is some linear differential operator, like the first derivative minus 3 times the identity, as I've written right here. So the crucial point is that if S is a basis for v, then the action of t on the basis determines the action of t on the entire vector space. Okay, and so the reason why is, let's see. Well, if I want to do t of u and see what t does to u, then I can write u in terms of the basis. So it's going to look like some sum of ci vi's, since this guy is a basis. Right, so being a basis means that I can do this this step right here, and that I know that this way of representing u is unique. There's only one way to do it. Okay, then using the fact that t is a linear transformation, I can switch the order, and instead of saying t of this linear combination, I can write the summation on the outside and the coefficients on the outside using my scalar multiplication and additivity properties, and say it's a linear combination of the t of v's. So this step comes because I know that t is linear. So that allows that. So now tu is determined entirely by t of v1 through vk. So this is what I mean by saying that the action of t on the basis determines the action of t anywhere.